Hello all, let's go ahead and start talking about section 8.3. This is where we're talking about the VSEPR theory. Remember that the VSEPR theory states that the repulsion between electron pairs, because electrons are all negative and they don't really want to be near each other, causes the molecular shapes to adjust so that the valence electron pairs stay as far apart as possible. Remember that they want to space out. They want to be as far away from one another as they possibly can. Remember that VSEPR or VSEPR stands for, stands for valence shell, starting in a bad place, electron pair repulsion theory. So it's right in the name. The definition is right in the name. Valence shell electron pair repulsion theory. Okay, so this chart should look familiar to you for those of you that were in my honors chemistry class. If you were in my general chemistry class, you should have also seen this. Obviously, I'm not expecting you to memorize all of this, but I hope it looks a little familiar. So what we're looking at here is the molecular shapes. So we just talked about Lewis diagrams, which are flat 2D structures. But we don't live in a two-dimensional world. We live in a three-dimensional world. And the shapes of molecules really plays a huge role in so many things. In the way that medical nanotechnology works, and the way that food science works. All of these things we'll talk about in the school year. I don't want to waste your time right now. So when we're talking about total domains, this is how many electron domains or electron zones are around the central atom. Those shapes are going to be linear. They have angles of 180 degrees. So for AP, things that are important for us are the total domains, what it's going to look like, the shape, the geometry, and the bond angles, as well as the hybridization. On your summer work, you need to list each of these things for me. So I'm just going to go ahead and do some examples, and you should have this as reference. If you Google VSEPR theory chart, you're going to see this same one. For those of you that were in my honors chem, you know we also did 5 and 6 electron domains, so keep that in mind. As we talk about this stuff in AP, we will obviously revisit it, but I want you to, when we do revisit it, to at least say, okay, yes, I've seen this before, and I'm familiar with it. So let's just go ahead and do some examples. So the first example is H2O. So the first thing we need to do is draw the Lewis structure for H2O. So I know this, and I know that a lot of you know how to do this, so I'm going to skip those steps again. Maybe. So it's going to be H-O-H with 2 lone pairs. So now we need to figure out how many electron domains are on my central atom and how many lone pairs are on my central atom. So electron domains are all the areas where there are electrons. So basically, oxygen can reach up, down, left, and right. How many of those areas have electrons in them? 1, 2, 3, 4. It has 4 electron domains, or 4 zones that have electrons in them. Now the next thing we need to look at is how many of those domains are lone pairs. There's a lone pair and there's a lone pair. So 4 electron domains, 2 lone pairs. And remember that a lone pair is just non-bonding electrons. So 4 domains, 2 lone pairs. Let's go look at our chart. So total domains, I know I have 4. Lone pairs, I have 2. So that's going to be this row and this shape. So it is bent tetrahedral, and it's going to look like this. So let's go ahead and draw that. So we have oxygen in the middle. I have my H. I have my bent. So notice I'm drawing it looking bent. And then I have my electron clouds. And you do not need to draw those bubbles. So really what your answer should look like is right there. And again, it has 4 domains, so we say it's tetrahedral. And since it has 2 lone pairs, it is bent. So tetrahedral bent. All right, the next one, carbon dioxide. So again, that one looks like this as a Lewis diagram. So let's go ahead and look at electron domains. So remember, electron domains are just the areas that have electrons on the carbon. So again, the central atom can reach up, down, left, and right. There are none top or bottom, but there are some here and there are some here. Now, even though those are double bonds, it doesn't matter. We're counting them as an electron domain. So there are 2 electron domains with 0 lone pairs on the central atom. So we're going to jump back. So we have, let me erase this for us. So we had 2 domains, 0 lone pairs. So that is linear in shape, and you can see it's going to look like this. So this is a linear molecule, so this is technically in 2 dimensions. It's just like a line. And it's still, linear ones are nice, looks just like that. They form a line. Next up we have BF3. Boron is one of the weird ones when it comes to the octet rule. Remember that hydrogen and helium have an octet of 2. Well, boron has an octet of 6. It is one of those weird exceptions. So the Lewis diagram, or the Lewis diagram here looks like this. And we can see that there are 1, 2, 3 electron domains with 0 lone pairs on my central atom. So let's jump back. So I have 3 electron domains, so I start here. 3 with 0 lone pairs is trigonal planar. So when I draw this out, think about it being in 3 dimensions. It's going to be flat. So when we build molecules of these, we'll be able to lay them flat on the table. BF3 trigonal. So guess why it gets that name? Looks like a triangle. And planar because it is all within one plane. Think about math class. It's all in one plane. No 3 dimensions here. And our last example is CCl4, or carbon tetrachloride. So I'm just going to quickly jump to my Lewis diagram. Okay, so on this carbon, we have 1, 2, 3, 4 electron domains with 0 lone pairs on the carbon. So that is 4 domains with 0 lone pairs, tetrahedral in shape. And this one we do have 3 dimensions, so notice there's a wedge and a dash. And hopefully you remember that that's how we represent things coming into the plane and out of the plane. So as far as carbon, we have carbon in the center. We have 2 chlorines that are going to be within the plane. And again, this will become more clear whenever we can build the molecules. One of those chlorines is going to be coming at us, so towards you, like out of the screen. So we represent that with a wedge. And then one of them is going to be back into the screen, which is going to be a dashed line. So this is, tetrahedral in shape. Tetrahedral in shape. So again, all we did here was take our Lewis diagrams and turn them into a 3-dimensional shape, and that is the VSEPR theory.